question asks, which of the following molecules can act as a Michael-donor? So first off, you really just need to know, what is a Michael-donor? A Michael-donor reacts with a Michael acceptor in the Michael reaction. And the Michael reaction is basically a 1,4 addition, where you're going to take basically an enolate and react it with an alpha beta unsaturated molecule. So the Michael donor is typically the nucleophile, the one that gets converted into an enolate. Almost always, it's going to have a methylene, which is a carbon with 2 hydrogens, and it's going to be sandwiched in between 2 electron withdrawing groups. Okay, so like a ketone, an ester, an aldehyde, a nitrile, for example. These are very common Michael donors. The reason why is because having an electron withdrawing group kind of sandwiching the methylene is going to make those alpha protons very acidic. It also makes them very stable, the enolate that we form. So having a stabilized enolate is important in order to kind of favor that 1,4 addition versus a 1,2 addition. And so if we take a look at our choices, we can see here very clearly that there's a CH2 sandwich between 2 electron withdrawing groups. Okay, so 1 is definitely capable of making that resonance stabilized enolate that we need for a Michael reaction to occur. So 1 for sure works. Number 2 is a little bit different. It doesn't really work as a Michael donor because we have 2 electron donating groups. And we also have 1 hydrogen here that's not acidic at all, because deprotonating it would make a very unstable kind of sp2 hybridized anion, or an anion on an sp2 hybridized carbon. So we can kind of cross off 2. If we look at answer choice 3, there are methyl groups, but we don't really have a doubly stabilized enolate. So we have a methylene group here and a methylene group here, but it's not going to be doubly stabilized because of the presence of kind of the second carbon atom. So the enolate that we would form in this case would look like this, but this is only a singly stabilized enolate because you can't push the resonance here because it's sp3 hybridized. So singly stabilized enolates typically favor 1,2 addition instead of the 1,4 addition that we need for the Michael reaction. So the answer to this question is A, 1 only.